Lab 2 Resistive Forces by Daniel Johnson, Kishore Sirigiri, and Matthew Williams.
So our research question for this formal lab was, how does the velocity of an object falling through a fluid relate to the fluid's viscosity?
So gravity accelerates objects at a rate of negative 9.81 meters per second squared regardless of mass or size. This holds true by the equation Fg equals mg. However, when objects fall through a fluid, they encounter a resistive force in the opposite direction of the force of gravity. Objects falling through a fluid experience a resistive force from the fluid they are falling through. This force limits the velocity that an object can reach in the fluid, also called the terminal velocity. This experiment examines the relationship between the resistive force from the fluid and the velocity of the object falling through the fluid. It was found that an object dropped in a fluid with a higher viscosity experienced a lower velocity.
Our experimental design used a ruler, graduated cylinder, and metal ball bearings. For our control, we dropped the ball in the air from a height of 0.117 meters. Our independent variable was the fluid type we used. Our dependent variable was the constant velocity. We filled up a graduated cylinder with 50 milliliters of fluid, that being corn syrup or water. We then dropped the ball from a height of 0.117 meters above the ground into the fluid. We would record the data points of the ball descending through the fluid and upload to the tracker software to get results. We repeated this procedure for the second fluid and control.
So variables and impact. So our independent variable was our fluid type and our dependent variable was our constant velocity. The independent variable was the type of fluid that the ball was falling through. This change of fluid would affect the velocity of the ball when dropped into the fluid. This impact was measured by the tracker software in terms of differences in terminal velocity and initial change in velocity from the initial velocity of the drop.
Resistive force and macroscopic friction. Both resistive force and macroscopic friction act on an object in the opposite direction of motion. Macroscopic friction has kinetic and static friction, while resistive force does not.
This is a model of our velocity versus time graph while the ball was dropped through the air.
This is our model for velocity versus time when the ball was dropped through corn syrup.
And this is our model for the velocity versus time when the ball was dropped into water.
This is our system schema having the ball, earth, and fluid. The ball is our system. The ball interacts with earth through gravity, and the ball interacts with fluid through contact.
So these are our energy pie charts. Before the drop, it has all gravitational potential energy. As it's falling, it has gravitational and kinetic energy. And once it's at the bottom, it has all kinetic energy. And since the pie charts are getting small, that indicates that there's a decrease in energy in the system.
So for our free body diagram, which demonstrates Newton's second law, we have the ball as our object, and then we have a force arrow representing the force of gravity from the earth on the ball pointing downwards, and another arrow pointing upwards representing the force of viscosity from the fluid on the ball. This free body diagram would represent once the ball has reached terminal velocity in the fluid, since the force of gravity is equal to the force of viscosity from the fluid on the ball.
Some of the flaws and limitations of our experiment were the viscosity change due to temperature, error in the tracking system, tracking of the ball not being precise, or error in the height of the drop.
So this is our scientific reasoning. We found that velocity is inversely proportional to the resistive force, which is viscosity. So to calculate force viscous, the equation is negative 6 pi beta RV. The radius of the ball was 0.5 centimeters, and the beta value that we got, the beta value for air was 1 times 10 to the negative fifth newtons per meters squared times seconds, and the beta for water was 1.0 times 10 to the negative third, and the beta for corn syrup was 5. So for velocity of the ball in the air, we got 0.51 meters per second, and for water we got 0.44 meters per second, and for corn syrup we got 6.9 times 10 to the negative 3 meters per second. We calculated this by taking the height of the graduated cylinder and dividing it by the amount of time it took for the ball to reach the bottom.
We were able to use all these values to calculate our viscosity for the air, water, and corn syrup. For the air, we calculated negative 4.81 times 10 to the negative 7 newtons, water was negative 4.15 times 10 to the negative 5 newtons, and corn syrup was negative 3.25 times 10 to the negative 3 newtons.